Perfect. Okay, so this is going to be a continuation of the multi-messenger talk that we heard the last time. But the problem in multi-messenger is like, the words are so long, gravitational waves, multi-messenger astronomy, the title basically becomes an abstract. So here is the shortened version, but in essence, the talk is going to be a continuation of what we heard in the last talk and, also yesterday. So we'll see. Well, I mean, it's a 101 quick intro and the things that I'll be talking about, the things that are important. So I think most of us are here to sort of learn about new physics or understand the fundamentals. Now, the way you do it is there are a couple of ways to do it, or even more than a couple actually. So we have the man-made accelerators like the LHC or the Tevatron, where people collide particles, you have beams, and then you try to study new physics. However, today I'm going to talk about this other aspect, which is the cosmic accelerators, the accelerators that nature has provided us with, where we have particle acceleration, and then from there we explore the different signatures. Now, just to give you a context, this cosmic accelerator, if you want to reach the energy scales that are accessible here, it's like building an LHC with the size of the orbit of Mercury. So that's the energy scales we are talking about. But the problem with this is these are black boxes. So here we can't really tune our beams and send it in and then try to see what we observe. So that is why we basically need to look at these messengers, which is familiar to everyone in this room, which primarily includes gravitational waves, cosmic rays, neutrinos, and gamma rays, or electromagnetic signatures. Now, gravitational waves, if you have a compact object, so for example, a merger, in that case, those are the main signatures. Cosmic rays, that's a whole different, maybe 1 hour, maybe 1 day long talk, the problems that are associated because of the magnetic fields that permeate the galactic and the extragalactic medium. So you have this deviation, so there's a whole puzzle in the cosmic ray sector. The EM signatures, well, they're good, but in the sense they can be obscured because of the dust or the debris that is associated with these phenomena. So, the hero of our story, neutrinos. So because they feebly interact with matter, so that enables them to sort of bring us the information from the heart of the sources, and that is why they're interesting. So today I'm going to specifically talk about high energy neutrinos, part of which you heard in the last talk. And in this high energy neutrino sector, we have had quite some progress in the last decade or so. So I'll very quickly go through it. So we already know the sources that we have seen evidence of. So for example, the NGC 1068, we have around 79 events with a 4.2 sigma significance. There is also the TXS, which is a little, I would say, a little more tricky than the NGC. And then there are a few other ones from which we have slight evidences as well. Then recently, these panels look really nice and beautiful, and we have seen most of them for quite some time now. But then the IceCube collaboration also added these three, where we are seeing the same galactic plane map, but in neutrinos. And from this also we have evidence of around 4.2 sigma over the background only hypothesis. So neutrinos from the galactic plane. The hope is eventually you'll be able to shrink these blobs and get a more precise sort of idea about the sources that are there in the galactic plane. So how does the high energy multi-messenger transient sky looks like? So particularly in the context of neutrinos and EM signatures. Well, you have things known as active galactic nuclei. So there's this supermassive black hole sitting in some sort of gassy medium, and it's basically accreting or eating up the gas that is surrounding it. These objects can have jets associated with it. And if the jet basically points towards you, in that case, you have something known as a blazar flare. And of course, this jet and the interaction with the surrounding material or the interstellar material is a rich source of neutrinos and EM signatures. You can have something known as tidal disruption events, where you have this supermassive black hole, and basically the tidal forces of the black hole shreds apart the star, the debris sort of infalls, and then you can have a jet associated with that as well, which also serves as neutrino and EM signature sources. Then you have the full sort of garden of supernovae, where you can have this engine-driven supernovae, where following you have a central engine, and there are shocks that are launched. These shocks can interact with the surrounding material and lead to neutrino and electromagnetic signatures. So for this, I won't go into detail. The talk this afternoon, I guess, will talk about these things in more detail. And then finally, you have the compact object mergers, where you can have these binary black hole mergers, or these binary neutron star mergers leading to the formation of a central remnant. You can have gamma rays and neutrinos associated with these objects as well. By the way, as you can imagine, this is not an exhaustive list, but this is just a few of the interesting candidates that I have worked on partly or I'm interested in. So it's a very biased sort of a list. Well, 170817, we heard about it yesterday and also partly today. So this was a BNS merger, and this was like the feather in the cap of multi-messenger astrophysics, where we saw this BNS merger event, and we sort of detected it in advanced LIGO and Virgo, and we also saw it in the electromagnetic signatures, in gamma rays, in optical, and in X-rays. But sadly enough, these are considered to be very good neutrino sources as well, but we did not see any neutrinos from this particular source. Given the distance, it's expected, but it would have been nice to sort of see neutrinos and add that to the picture as well. So since I'm talking about this high energy neutrino production, so let's just very quickly go over this. We saw it in the last talk as well. But if you consider the hadronic channels, you have PP or P gamma interactions leading to the production of charged or neutral pions. And then these pions decay to charged leptons and neutrinos, the charged ones. And then the neutral pions basically decay to give the gamma rays or the EM signatures. So what are the conditions, okay? So firstly, because you need to sort of accelerate the proton or the hadron in this particular case, you need an environment where this particle acceleration can happen through, for example, shocks, magnetic reconnection. You can have turbulence leading to stochastic acceleration or phenomena as such. Okay. Next thing is basically you need the rate of acceleration to be greater than the rate of energy loss. Else you can accelerate them as much as you want, but they lose energy and you basically have nothing. So to quantify that rate, for example, if you consider PP, so this is the rate where it depends on the nucleon density, the elasticity factor associated with the proton, and then also the cross section. Similarly for P gamma, it's a little more complicated because here you have to take into account the photon energies as well. Okay. So that basically leads to the third point, that is you need a radiation field or a radiation bath or a bath where you have these protons so that these accelerated particles can then interact and then lead to the production of the high energy neutrinos. So I'm going to talk about this particular scenario, that is BNS merger, and in particular a stable remnant from a binary neutron star merger. So why are they interesting? Why should you care about BNS merger? I mean, I think everybody does, but here is just an overview for that. So here is BNS sitting in the center, the BNS merger. So in gravitational waves, we basically observed it already from 1708-17, and hopefully in the future we'll observe more of them. In electromagnetic channels, we also saw the kilonova emission associated with 1708-17 and the afterglow emission along with the short GRB as well. So this has also been observed. BNS mergers are thought to be efficient particle accelerators as well. So for example, this is a plot of the magnetic field strength with the co-moving side, and this is generally known as the Hillas condition. That is, the Larmor radius needs to be less than or equal to the size of the accelerator itself. So just to sort of quantify it, these are the lines for two different values of the velocity normalized to the speed of light. So anything that lies above this line will be an efficient cosmic ray accelerator or particle accelerator. And you see that depending on what sort of models you choose, they do lie above, which basically hints towards them being good particle accelerators. And then finally, as I said, they're thought to be rich neutrino, high energy neutrino sources. For example, you can have neutrino production in these objects, in the jets, or you can have neutrino production in stuff that I'll talk about for the next part of my talk. So this is a plot that you will see in a little bit. So the main takeaway message from this slide is that BNS merger is a multi-messenger zoo, or you have all of this sort of fitting together to give you a source that is of interest. So my talk is sort of divided into two parts. We'll see, I think I should be able to go through both of them. The first part is fresh out of the box. This is on the archive today. And the second part, I have the results, but I mean, if you're interested, I can discuss, but I'm not going to present it here in this talk for this one. Okay, so let's get started. So here is a binary neutron star merger. So once you have the merger, you can have various scenarios. So you can have a prompt collapse to this black hole system where you have this black hole torus and a jet that is associated. In some cases, you can have this sort of hypermassive or supermassive remnants. If you have it to be hypermassive, it then collapses to a black hole on dynamical timescales. If you have it supermassive, it can either collapse to a black hole in sort of, order 10 to the power 5 or 6 seconds, or you can have this stable neutron star, which is what I show over here. Now, it's wrong to sort of think that there is this particular sort of 1.2 MTOV that is the mass limit. It's sort of like a spectrum. So just like in core collapse supernovae, you have a spectrum between the failed and the successful supernovae, and similarly here, it's also a spectrum. And that spectrum basically depends on the equation of state that is associated with the neutron stars, the mass, the spin, and factors like that. So as I said, I'm going to focus on the stable remnant from a BNS merger. And here is the model. There's a lot sort of happening here, so let's go over it slowly. So this blue blob over here is the magnetar. It's the remnant. And because the magnetic fields that are associated over here are dipole, at the dipole, it's around 10 to the power 13 to 15 Gauss. So these are like really high magnetic fields. So what happens in the polar regions is because of these high magnetic fields, you can basically pull out charges or ions from the crust of the neutron star. And once you pull out these charges, they suffer acceleration because of this magnetic field, and this is a site of efficient particle acceleration. Also, because you have this sort of system, you have the rest of the debris from the merger that is sort of slowly expanding outwards. And eventually, because of this magnetosphere of the ionized plasma that you have over here, you have something known as winds that are sourced from this magnetar. Now, this wind basically is associated with this shock structure, that is this red line that you see over here, which is what we call as termination shock. Now, eventually, as this system evolves in time, what happens is a part of the ejecta gets highly ionized, and it has tons of E plus E minus pairs, and this is the region that we call the nebular region. So this region has E plus E minus pairs, it has thermal, non-thermal photons, and all of it is in there in the nebular region. And then following that, you have the ejecta, part of which is mildly ionized, and then part of which is neutral, which is this thing over here. Now, so that's the sort of the parts of the model. So let's see what's exactly happening over here. So the charges get pulled out from here, they get accelerated. So that's one site of particle acceleration. And also the termination shock region, because of magnetic reconnection, you can have particle acceleration in this region as well. So there are two sites of particle acceleration. So once these protons are accelerated, they then go into this nebular region and they find the photons. And as I mentioned before, they do P gamma to produce charged pions, and then these decay into neutrinos eventually, and you have these neutrino signatures. Also, as is evident from the figure, these are rich sources for EM observations as well, because you have these non-thermal photons to begin with in the nebula. These non-thermal photons get reprocessed by this nebular ejector sort of that region. I won't call it a boundary because it's not precisely a boundary, but sort of this region, and they get converted into thermal photons, and that's how you have the thermal photons in the nebula. And then eventually these photons sort of diffuse out, giving you the EM signatures that are associated with such objects. One interesting thing, that paper is also on the archive today. So Fermilat eventually saw one of these superluminous supernovae and like a GeV gamma rays from that source. And the hint is towards it being, it's a superluminous supernovae, but the central engine could be a magnetar powered engine, which also makes this whole paradigm very interesting. Okay, so now let's go into the details of the physical quantities in the model. So the magnetar is basically, because of the conservation of angular momentum from the merger itself, it's spinning around. But eventually, sort of the spin of the magnetar, that energy that is associated with the spin, that is distributed in the non-thermal, thermal, and the magnetic energies. So let's look at the non-thermal energy first. So the way this evolves in time is it's directly proportional to the spin down luminosity. So as the magnetar slowly sort of spins down, the energy gets deposited in this non-thermal energy component. The second term over here is the PDV work that is done by the nebula. So this whole thing is expanding outwards, as I mentioned. So that's the work done. So that basically gets subtracted. The third thing here is basically these photons that I mentioned, they eventually diffuse out. So that basically takes away from the non-thermal component. So you have this term that is subtracted from the whole thing. Okay, now let's look at the thermal energy. So to begin with, there are no thermal photons in the system because it's all non-thermal. Eventually, what happens is you have these reprocessing, as I mentioned, on the junction of the nebula and the ejecta, and a part of the non-thermal photons is converted into thermal photons, which is accounted by this term over here. The second term is the same, it's the PDV work that is happening at the ejecta. The third term is these thermal photons also eventually leave the ejecta and they diffuse out. As the system evolves in time, the optical depth goes down. And finally, this term over here is the heating rate due to the decay of R process elements that are there in the ejecta. So this you heard talks yesterday about of this in a lot of detail. So we take into account this as well. But I would not go into the detail of this because for the parameter choices that we choose, this term is not really relevant for us. But you can ask me about it and I can talk about it. Okay. Then the third component, which is the magnetic energy. So this is also directly proportional to the spin down luminosity, that is this LST. And then it also sort of, the constant of proportionality is this magnetic field strength amplification factor that happens in this system, which is ordered this 10 to the power minus 4 number. Now you might ask, okay, how do I just pull out this number out of the hat? Because it's sort of, so it's motivated by the observations of the Crab Nebula. So in Crab Nebula, this number is sort of the order 10 to the power minus 6. But in general, people believe that this is this strength amplification is order 10 to the power minus 4 number, and you can also sort of get to these numbers from particle in a cell simulations as well. And then this term over here is once again the work that the magnetic field does in pushing the whole thing out. Finally, the whole thing is sort of evolving out, so you have to look at the kinematics, and this basically is work done on the ejecta, which is a summation of all these three energies depositing the energy to make the whole system move out. So then, let's look at the plots because those are more interesting. So you have the energies on the y-axis and the time since the merger on the x-axis. And I consider two different cases. One is a fiducial case, which is sort of motivated by a 1708-17 sort of object. And then the other is a much more optimistic case. So the main difference over here is you see that the spin period is sort of lower, so it's spinning sort of faster. So therefore, you have things that are shifted by roughly an order of magnitude in this optimistic case. I also show three different sort of time scales. So this blue line is the spin down time scale, which is sort of depending on the strength of the magnetic field at the polar region and also the spin period of this particular object. And then the LST is the spin down luminosity, which basically depends on the dipole moment and the spin period, which is 2 pi over pi. So this is omega, and then c is the constant. So what you see over here is, if I look at the spin down energy, it peaks around the spin down time scale, which is obvious. And then post that, it sort of goes down. The non-thermal component, it sort of follows the spin down because that's the main source. As I said, it's proportional. So it roughly follows the spin down energy as well. The thermal component, it peaks somewhere in between, but then you see that once this sort of diffusion through the ejecta becomes important, so you have a very steep fall off because your photons are diffusing out because it's optically thin. This EP I'm going to talk about in a bit, not now. And then finally, the magnetic energy, because it is also proportional to the spin down luminosity, that also goes similar to this EST. Okay. So now that I've discussed the sort of physicalities that are associated with the system, let's sort of start our journey on the main aspect, which is how do we get neutrinos from this? Well, so the first thing is you need to pull out charges. So that happens at the polar cap region, as I said. And we consider this Goldrich-Julian sort of number density of charges that are associated. So what happens is because of this really high magnetic fields, this is thought to be a good conductor. So you have electric fields that are generated, and that pulls out charges from the crust of the neutron star. So that number density was calculated a long time back in 1960s, and that's given by the Goldrich-Julian charge density. Okay, so once you have pulled out the charges, you're happy, and now you want to accelerate them. Two sites, the polar cap and the termination shock region. So these cosmic ray protons need to be injected for them to be accelerated. So the injection spectrum in this sort of a polar cap region follows this sort of a Dirac delta distribution, which depends on the energy of your proton. So of course, this is this term over here. And then the cutoff energy that is associated with the spectra, which is this term over here. So how do you calculate the cutoff energy? So let's look at that. So this cutoff energy is decided by the maximum energy in the polar cap, which is this PC, and termination shock region, which is this TS. So for the polar cap region, the cutoff energy depends on two things. So one is, as I said, there is a potential gap that is created. So a fraction of that potential gap is used in accelerating the particle. So that's given, that fraction is given by eta gap. And then basically this quantity is what decides your maximum energy in the polar cap acceleration, so which is this EPC max. But then you also need to remember, because this is a charged particle moving through a magnetic field, it will lose energy. So the energy loss due to the curvature radiation is given by this E curve over here, which is this quantity that I show. If you look at the plot over here, so I plot the proton energy on the y-axis with the time since the merger on the x-axis. So let's look at the behavior. So for EPC max, so you can forget about the optimistic case. It's like a different case. So let's look at the fiducial case for the time being. So for the EPC max, you have this dashed curve. So you see it's sort of constant until the spin down, and then post that it goes down. I mean, that is sort of easy to see because it is associated with the P, which is the spin period. So as the spin period sort of goes down, you have this decrease in the curve. For the curvature radiation, it is fixed up to a constant, I mean up to the spin down period, and then it sort of increases because it's inversely proportional to as the object is spinning down, this curvature radiation eventually goes up. Yes? Yeah, so this is the injection, and then we solve the full cosmic ray transport equation. So I'll come to that. Yeah, but I don't see that. Let's say that I take the limit of the charge is 0. How does it disappear? It should disappear. So limit of the charge being 0 in the sense you mean that you don't inject anything at all? Yeah, for example. I don't see from this equation. So for example, I mean, I'm having a hard time understanding a question. So you're saying that this one over here? Yes. So there is no coupling between this left-hand side and right-hand side. There is another function that I can decide. Right. Yeah, energy of the proton, yes. So then how this n dot disappeared in the limit of the zero coupling? So EP is 0, you mean? But it's so if EP, I mean, so you only have this to be a non-zero number in that energy range that you're taking, right? Because this is a delta function. So else you will just have 0 that is associated with this function, no? Yeah, yeah. So then you won't have anything at all. And that's, I mean, so people consider, for example, you know, depending on where you're trying to pull out particles and accelerate them, you can have different spectra. For example, you can consider like a power law spectra, which is what I'll be talking about in the termination shock region. But it has been shown that for these polar cap accelerations, delta function is sort of your injection spectra. So then it just gives you 0 except for that small band where you want to accelerate the protons. Yes. So n norm is just the normalization that is associated. So you need to normalize this because this is a distribution. So you need to normalize it to something, right? So the way you do that is you basically decide on a luminosity and you say that, okay, my proton luminosity could be, you know, maximum this, and then you use that to normalize this thing. It's not really arbitrary because this NP dot norm, maybe I should have put the expression, it is associated with the maximum amount of charge that you can pull out from the surface, right? Because if you integrate the full spectrum over all energy, that should give you the total number, no? Because this is a number density, right? So it's not arbitrary. It has a particular thing that is associated. Well, I mean, it depends how do you define a lot. It's very, so it's like you have the spectrum and you integrate it and you get a number, and that's given by the Goldrich-Julian. So that's basically, you know, this number that you get. So if you do n dot p times t, that gives you a total number, right? So if you integrate the spectrum over energy, that should give you the total number. Okay. Okay. So we sort of finished off with the polar cap acceleration. Let's talk about the termination shock. In that case, there are two things that are associated. So you have to balance the rate of acceleration with the rate of energy loss. So the rate of acceleration is, once again, you have this coefficient that is pulled out from particle NSL simulations. And the rate of energy loss depends on the escape of your protons because they diffuse out of your system. And then also the cooling time scales that are associated. So in the cooling time scale, you have basically PP, P gamma, synchrotron, Bethe-Heitler, and the dynamical losses that are associated. So you do all of that, and then that basically gives you this curve that you see over here for the fiducial case. And the main takeaway message from discussing all of this is the final cutoff energy doesn't really care about the acceleration at the termination shock for our parameters because you see this is always much less. So in this particular system, we only have particle acceleration in the polar cap region. Okay. So once you have done that, you compute the steady state cosmic ray energy spectrum, which is given by this equation over here. So it depends on the injection spectrum that I discussed. And then it also depends on the cooling and the escape timescales that are associated. So you do all of that, and now I'm in a position to talk about this thin line that you see over here. So that's the total energy that is associated with the protons, and you can see that two peaks around the spin down time scale, and then it eventually goes down, and you get all of this by solving the transport equation. Okay, so now you have done your whole thing with protons, you have extracted them, you have accelerated them, so now I need a photon field. So how do I get that? So I consider this E plus, E minus spectra that I show over here. So this basically goes as a power law. So until some break Lorentz factor that is associated, you have it to be around minus 1.5, and then post that you have a much softer spectra, which goes to minus 2.5. Now this break Lorentz factor, once again, from Crab observations, Crab nebula observations, is around a 10 to the power 5 to 10 to the power 6 numbers. But then what happens is in a general system, if you consider pair injection, this number is sort of low, so here we choose it to be 1,000. So these details I'm just providing in case someone has questions. But you have a spectra, you once again do the transport equation for the electrons, you go through the whole electromagnetic cascade, that is you do synchrotron, inverse Compton, Bethe-Heitler, and that gives you the photons that you see over here. So all of this is consistently done, and then if you ignored the talk until here, this is the main takeaway slide, and this is of importance. So what do you get from the neutrino fluence after doing all of this? So here are the results for the fiducial and the optimistic cases. On the x-axis, I have the neutrino energy, and on the y-axis, I have the neutrino fluence. And this is for a typical source at around 40 megaparsecs, so 1708, 17 sort of a source. So let's look at the fiducial case first. So here, the peak fluence is around 10 to the power minus 2 GeV per centimeter square. And the energy of neutrinos where it sort of peaks is around 10 to the power 7 to 8 GeVs. For the optimistic case, of course, because it's optimistic, so you have a higher neutrino fluence that is associated with this particular model. And it primarily has to do because you have a higher proton energy, so you have more sort of accelerated protons that can produce more neutrinos. Okay, so now what you see from this plot is that, given even the next generation detectors, this doesn't really reach that sort of limit, right? So how do we actually see these neutrinos? So that's what I'll address in the next part of my talk. So one more takeaway message is you also need to notice when do we have the peak in the neutrino spectrum. So for the fiducial case, we have the peak around 10 to the power 5.5 to 10 to the power 6 seconds, which is order a few days post the merger. In case of the optimistic case, it's around a few tens of days to a month post the merger. And this information will become important in the later part of my talk. Okay. So just to understand the neutrino spectrum, why does it behave the way it behaves? I've shown here the different time scales that are associated. So this is an initial time scale where you see that the photomeson, that is the P gamma interaction, sort of is the main cooling channel. So that's very efficient for neutrino production. So therefore, you have the thing to be rising. But then if you look at a later time snapshot, you see that the cooling is sort of not really dominated by P gamma. You have this blue curve that is that is a bit lower. So therefore, you eventually have the neutrino spectra that it falls off. The other important thing is, of course, you have to look at pion suppression or pion cooling, because if they cool faster before producing the neutrinos, you won't really have the neutrino production. So in this particular plot, I show the pion cooling aspect. So once again, this is time post merger, and what you notice is anywhere where these sort of dashed curve is above the solid curve. So those are the regimes when pion cooling is not important. So you see that right from starting from the early times, pion cooling is not that important, and therefore, we have efficient neutrino production in these sources. Yeah. Yes.
So when you are trying to get trying to basically pull out the charges from the polar region, polar cap, so you are taking a diamagnetic field.
Yes.
And where do you cut because it's some special variations.
Right. So basically, because I'm only focusing on the polar cap region, so I'm only sort of looking at that region where we think that the magnetic field is strong enough where we can ignore the spatial deviations. Because try to understand, it's not like I'm pulling up from the equatorial plane. It's just in the polar region. So there, the field is sort of strong enough that we can ignore the spatial variations in the field.
But in general, if you consider the whole, then you should.
Well, the problem is in equatorial region, so past the light cylinder, the field falls off as 1 upon r square, and there you won't have a strong field enough to pull out charges from the crust. So you can only do it in the polar region. Yeah, in the cap region, yeah. Okay. So the other interesting part that people do look at is the diffuse neutrino flux that you can get from these models. So here I have plotted the diffuse flux for the fiducial and the optimistic cases. But then you have to also remember that these sort of stable remnants, it's not like if I have a BNS merger, it will form stable remnants all the time. So therefore, based on literature, the assumptions are pretty conservative that we claim that around if 10% of the remnants are actually stable, in that case, this is what you would get as the solid lines. And if you sort of crank up the number all the way to 1, which is of course unlikely and unphysical, then you would get the band that you see with the upper limit. But the good thing over here is if we do have like a low spin period of like 1 millisecond or so, in that case, the future ice cube or this grand, I'll talk more about grand towards the end of my talk, might be able to see some of these neutrinos from the diffuse flux. But the contribution is very low. It's like 1 to 10% of the net diffuse flux. Okay. So you saw that, yes. Really? Oh my God, okay. Well, I'll speed up. Yeah, okay. So as you can see that after doing all of this, it's very hard to sort of see these neutrinos. So here is a strategy of how do you actually use the GW observations to sort of do these triggered searches for these neutrinos. So in very short, you have these next generation planned GW detectors like the Einstein telescope or the Cosmic Explorer, along with the next generation neutrino detectors as well. So the idea here is performing like a triggered stacking search, where let's say you have this sort of GW signatures in the GW detectors, you go back to your neutrino detector data, and let's say you have mergers at T1, T2, T3, and so on. So you have a time scale of this neutron emission that is associated with the merger, which is what I showed in that plot, for example, 10 to the power 6 seconds post the merger, and you have these windows. So you can make these cuts in your data, and then you can search for neutrinos in these windows. And this hopefully will sort of lead to a reduced background because you're not looking at the full data, but you're only looking at the data in these windows. And that allows you to search for signal events. So this is the idea of a triggered stacking search. But the problem is this next generation detectors, as you can see from this particular plot, are sensitive to neutron star mergers from very high redshifts. So them being sensitive to very high redshifts, plus the uncertainty in the neutrino emission associated with BNS mergers, basically screws up this triggered search paradigm because now you don't know the size of these windows and you have like tons of triggers because of their sensitivity. So then the question basically boils down to, okay, how do we find meaningful triggers to then perform our high energy neutrino searches? So a way to do this, I mean, there are several ways, but one way to do this, you basically can look at the sky localization capability of the gravitational wave detectors. So how do you basically do this? Let's say you have a trigger, and then post that trigger, you have various other mergers that go on in your sky map. So you add the total area that is covered by these localization areas, and you divide by 4 pi, that will give you a fraction. Then you can set a threshold that, okay, at any point in time, my threshold sky fraction covered is, let's say, 1%. And then that gives you an upper limit or a distance cut from which you accept meaningful triggers from your gravitational wave detectors to then perform the searches. So here is the localization capability of these next generation detectors with luminosity distance. And of course, Cosmic Explorer, because it's like one arm, so it does pretty poorly. Einstein telescope can do the triangulation, so it does a little bit better. And then the best case scenario is the combination of both. On the other axis, I have shown the BNS merger rate, where this solid line is assuming 300 per gigaparsec cube per year as the fiducial rate. And then given the current LIGO data, the whole window is starting from 10 per gigaparsec cube per year all the way to 1700. So there's this huge uncertainty window associated with the merger rate. But okay, this quantifies the idea that I was talking about. So for example, you have the luminosity distance on the x-axis, and this is the fraction of sky area covered given the localization capability of the detectors. So as you see, as sort of my luminosity distance increases, these go up, the fraction goes up. But then if I choose a particular threshold, given a time window of 1,000 seconds, then it sort of gives you that, okay, the limiting distance, if I use, let's say, the combination of Einstein telescope and Cosmic Explorer, that's around 2 gigaparsec if I choose a threshold of around 0.01%. If I increase the threshold, then basically you sort of shift this way. and your limiting distances increase. Okay, maybe I'll come directly to the results because I don't have enough time. So in these plots, what I've shown is the time scale of operation for these joint neutrino and gravitational wave detectors, along with the probability of a neutrino detection on the y-axis. So the way to read this plot is basically, if you look at this particular line associated with Cosmic Explorer, so it's telling you that you have a probability of around 95% to see a high energy neutrino source in a time scale of joint operation of around 10 years. However, if you do not see a neutrino, in that case, you can put constraints on the parameter space at 2 sigma also in a time scale of around 10 years. So these upper panels basically show the results for Cosmic Explorer, Einstein telescope, and the combination. And the band basically shows the variation in the energy that is emitted in high energy neutrinos. The lower panel shows the same band, but the time after which the neutrinos are emitted. So if it's very short, you do very good because you have less number of background events in the window. And if it's very long, in that case, it will take you much longer to read the same results. So just the takeaway message from this particular plot is, if you in case have the combination of Einstein telescope and Cosmic Explorer, in that case, even for the most sort of pessimistic cases, that is, it's a very low energy or it takes like really long, in a time scale of around 20 years, you can still sort of do some sort of a promising search for these sort of neutrino signatures from these sources. So these are the results from the model that I talked about, that is these magnetar models. So for time constraints, you can ignore this because this shows the case when 100% of them are magnetars. If that's not true, for a more realistic case, you see that using the combination and the optimistic scenario, in around 20 years, you can have a 95% probability to see a neutrino from such a source. If you do not see a neutrino in 20 years' time, in that case, constraints can be put at the 2 sigma level on the parameter spaces. I think the final thing before I end. So this sort of a search is also not background free. Like as you were seeing in the last talk, so there are these atmospheric backgrounds, conventional, and then the astrophysical backgrounds are as well. So it's not like you can arbitrarily choose the fraction of threshold that you cover or the operation time. So it's sort of constrained depending on what sort of backgrounds you're looking at. So for example, if let's say the background associated is around 10% with your search, then what this is telling you is that if you want to sort of search for these things in a time scale of 10 years, then you're supposed to choose your threshold as around 0.1% or so. So that's the main takeaway message. And you can repeat this analysis, but for radio neutrino detectors, which are being planned in Europe, for example, this GRAND, or the one that is already operational, which is this RNOG, which looks for this Askaryan effect with neutrinos. So using that, you can sort of put constraints. This is the same parameter space. So this is the energy in high energy neutrinos versus the time after which they're emitted post merger. And in this case also, you sort of see that, in a time scale of, less than 5 years or so, you reach decent enough results in these sort of searches by combining GW and neutrino observations. So yeah, with that, I come to the end of my talk. Just a nice plot. So this is how the sky is going to look like in the era of when we have these radio neutrino observatories to do these searches. Here is IceCube Gen 2 radio, if that happens. Here is RNOG, which is operational right now in Greenland. And then this is what the proposed GRAND detector would see in the sky. So you see the sky coverage is pretty nice. And that brings me to the end of the talk. Thank you so much for having me here. And
time for questions, comments, curiosity.
So I have just naive question about do you have any left top plot like muons or hyperons contribution?
muons are, sorry, what?
Hyperon,
Well,
like a strange variant. So
well, yeah, you can go to that route. For example,
I don't know whether it's relevant. But is it obviously negligible or?
No, it's not. It's not that obvious if it's negligible.
If you have a hyperon, you have a kaons and so on, right?
Right. So you can have that whole channel, and I think people have looked at it, for example, in the context of atmospheric fluxes, where you can have these charm decays leading to considerable atmospheric flux. But here in this model, we didn't really take that route. We assumed that okay, we are just limited to the normal muons decaying into the pions decaying into neutrinos. We didn't really take that route to explore.
It's not too obvious that.
No, it's not too obvious. No, at least not that I know of. Yeah.
So I understand your main result is the spectrum of neutrinos. I mean, and then you suggest this window of energy of 10 to 100 PV, which is probably most somehow likely for one to be somehow targeted. But I wonder why you don't try somehow an estimation of how many events of this type you have. I understand that there will be significant uncertainty, but I mean using, say, astronomy and possibly these events which was seen, do you have some number for the number of expected such events?
Yeah, so you can, I mean, that number is very easy to calculate, right? So you assume a fiducial rate, which is, let's say, 300 per gigaparsec cube per year. You multiply it by the volume, the co-moving volume, which is, the integral 4 pi r square dl. And so this, for example, this particular result is for 40 megaparsec. So you put your luminosity distance to be 40 megaparsec, convert it with the redshift to co-moving, but this is pretty near, so you can ignore that. So that will give you the total number, which I have not done in my head, but that will give you the total number. And then you sort of claim that, if I assume 10% of them to be these stable remnants, because as I said, the expectation is not that, you would have a lot of them. So that should give you like a particular number. I did do this calculation, but for where I was looking at redshifts, like much higher redshifts. So there you would find like around 4 of these sources a year within like a distance of 3.5 gigaparsec. So that's the number I have in my head. So it's like, it's not a lot, it's like...
No, it's good, I mean, just very reasonable.
Yeah.
That's it. Then a comment, I mean, Franco Pacini is the guy who created this concept of, say, neutron star. It was just from here, from this place, Florence. No, I mean, just to remind that this is not irrelevant for your somehow talk.
Yeah.
Thanks. Careful.
I have a general question. I mean, so far in the study of black hole merger, or supernova black hole, or supernova mergers, no experiment has seen any sign of neutrino so far, as I understood. So my question is, are you worried of this? Because they start to have good statistics. No, I mean, at least in the black hole merger, the statistics is not so bad. So
Yes,
what's your point of view on this?
So black hole mergers are not thought to be ideal high energy neutrino sources. Because try to understand, in the sense that the high energy neutrino production requires that you have this sort of radiation field or this proton bath through which you can interact, right? Here you do have it because you have the material of the two neutron stars that gives you that medium, where if you have jets or if you have shocks, everything can interact with that debris or with that ejector. For BBH mergers, because you have like sort of two black holes, you don't have that material through which you can have these interactions and then lead to high energy neutrino sources. However, people have proposed this, and I was just talking about this at the break, that you can have these binary black hole mergers in the disk of an active galactic nuclei. So then you use the material that is there surrounding this gas in this active galactic nuclei, and then you can claim that, you can have neutrino sources, but such a search has not yielded anything. I am also sort of developing a pipeline to do that search, but the result will be null. That is pretty obvious. So it's not worrisome. What would be worrisome is, for example, you have these next generation detectors, and then you are seeing BNS mergers, but you're not seeing any neutrinos. That would be worrisome because BNS mergers are thought to be, rich sources of these high energy neutrinos, depending on what we have currently. But for a BBH merger, that's not really the case. So I wouldn't be that worried that, we haven't seen anything from the BBH merger sources. And currently, most of the data that LIGO has is BBH merger. We have only a couple of BNS.
Yeah, so far there is not so much.
Exactly. So we just have a couple. I mean, they unblinded the 3.2 data set, and there also they basically have nothing of the BNS sort. So it's not that worrisome.
Yeah, Alexei, can you?
Maybe I'll just
It's okay. No, it's okay.
the properties of this say position of maximum.
Yes.
So there are some parameters, right?
Yes.
So I'm asking what determines really the properties of this
Right.
spectrum. So what is the size of the magnetic field you are assuming, right? So what is the size of the region of acceleration? So there are many parameters probably, right, involved.
Yeah. So is it okay if I write it here, or I can? So basically, so if you want to do, let's say, a back of the envelope estimate, right? So this is all numerical codes, like which we wrote. But if you, so it's basically, okay, I hope it's visible. But if you want to do a back of the envelope estimate, so you have the three, because you have the three flavors, and it's 1/8 of the energy of the proton. So to answer your question, whatever goes in is through this energy of the proton. So that's one thing. And then there are all these, fudge factors or correction factors, where this is, for example, the bolometric correction, this is the pion suppression, this is the efficiency of the P gamma process. Now, the efficiency of the P gamma process is where, so what I'll do is I'll detail the parameters which goes in where. So for the P gamma process, when I showed you the acceleration quantities, so all those parameters go into deciding this efficiency of this P gamma process. The pion suppression I already showed, so that depends on your individual proton energies and how they compare with the pion cooling time scale. Bolometric, it depends on the spectra. For us, it's basically one, we check that. So the rest of the physical parameters, that is, that is the polar cap acceleration or whatever other things I talked about. So those physical parameters goes in deciding the net energy that is given to the protons.
Also flux of these protons.
Yes. Yeah, so the flux, all of it goes in, because the way you do this is you write, right? So you have the injection spectra that I showed you. So that,
Just since it's kind of lunchtime, I
yes.
don't want to.
Yeah, so
We can continue, but can you say, so what is this, the maximum? Just say what are parameters? Size of magnetic field, what are parameters?
okay. Yeah, so the parameters are the size of the magnetic field in the polar cap region, the spin period of the whole object, and the efficiency of the acceleration. So these are the three, and the efficiency is something that you pull up from the microphysics of plasma. Okay. And then these are the three main parameters that decides where this peak will be.
Maybe the microphone should be there.
Last question. You consider the P gamma process as the main source, but in principle, even the gamma process can templates and produce neutrinos. Do you have it in your calculation?
No, because my nebula is the radiation, it's a very rich source of these sort of, you have the gammas. So therefore, we check the PP and the P gamma, but we didn't go through the gamma channel producing to neutrinos. But as far as I know, I think the contribution would be.
It depends on the energy. If the energy is very high, you can have neutrinos even from the
That is.
depends on the energy.
But I do not know how it will compare with the P gamma process. So maybe that is something that I should check. But here we checked PP. PP was not at all relevant. P gamma was.
Yeah.
So those are the two things that I checked. Yeah. Yeah, that's, but yeah, and that is what I would think as well.
Other, yes, Gunther. Yes, please.
Maybe I misunderstood, but in your
So,
injection-
sorry, it would be good if you share your okay, Gunther. They are discussing. No, please. Please go
I
ahead.
think in some of your equation you had a delta in that you inject the particles at one particular energy, which is the maximum energy, or did I?
Yeah, that's a good question. So yeah, I have the delta function, but it's not like one energy bin, it's like a window. It's like
okay.
And I have checked that, if you vary the size of the window up to 20%, 30%, the results do not change. And the reason I do that is because, back in 2003, there are these papers which showed that the particle injection in case of a polar cap acceleration would be a delta function window. Unfortunately, I had to do the whole analysis assuming a spectra as well, and that really didn't lead to anything. So
Thanks.
Other comments or questions? Okay, let us thank the speaker again. No, that's perfect. Lunch at 1, not before, and we reconvene at 2. Okay? So enjoy.
Yeah, I don't know.